Okay, this bell work kind of reviews all of the theorems that we've learned so far in this unit about circles. So this first question number one, the first few kind of deal with the first section. So up here in the directions, it says all lines that appear to be tangent are tangent. That's kind of important because remember our one theorem said that if we came, it was a diameter, or if we went, from the center to a point of tangency, then we know that that is perpendicular. That's going to help us solve these problems because now we know we have a right triangle. So to solve that, I'm going to set up my right triangle trig, and I think I'll use tangent. So tangent of 21 degrees equals opposite over adjacent. I'll do the algebra on that. So x equals 11 times the tangent of 21 degrees. So x turns out to be, type that in, 11 times the tangent of 21, 4.22. So whatever our units are, 4.22 units. Okay, over here, same thing. Looks like I've got my radius is going to a point of tangency here, so we've got a right triangle. This is 60 degrees, so I think I'm going to use my special triangle patterns. I could do this with a trig function, but I'm going to do this with our special patterns, our 30, 60, 90 patterns. So I'm given this side right here of 21, which happens to be the side across from the 60. I always want to find the smallest side first, so I want to get to that side right there. It happens to be our x. Well, this right here, if we were going to put in our labels, this is the 2x ratio, x, and x root 3. So I'm going to take the 21 and divide it by the square root of 3, and that's going to give me that side I'm looking for. So 21 divided by the square root of 3, I'm going to rationalize that, and we end up with 7 root 3. So my answer is 7 root 3. So once again, if you wanted to do a trig function, some of you guys have the calculators that will give that to you as a radical. So if you did tangent, you could say tangent of 60 degrees equals the opposite side over the adjacent side. So x is going to turn out to be 21 divided by the tangent of 60 degrees. So if you just type that in, 21 divided by the tangent of 60 degrees, it gives you 7 root 3. Or if you don't have that nice calculator, it gives you as a decimal of 12.12. Okay, third one over here. I'm going to do my 45-45 patterns again. It is a right triangle. We've got our point of tangency right there is 90 degrees. If it's a 45-45, these two sides are the same. So we've got 8 here and 8 here. So that means I'm just looking for the hypotenuse. It's kind of hard to tell on your paper, but that x is going to be from the center of the circle to the edge of the triangle. It's the hypotenuse of that right triangle. So if I'm looking for the hypotenuse, all I do is take my 8 and multiply it by the square root of 2. So my missing side is 8 root 2. You could set up a trig function to do that, but it's quicker if you just use your special patterns. All right, these three down here. Remember we had that theorem that said that if you have a exterior point and you have common tangents that go to that point, then these two segments are equal. So 3x plus 10 equals 7x minus 6. We'll do the algebra on that. We get x equals 4. Okay, over here, this is kind of reviewing our central angle theorem and our arc measures. So these look like they're all central angles because the vertex of all of these angles are at the center. That's why it's called a central angle. So this arc measure out here is 55 degrees. This arc measure is 21, so its central angle is 21. Don't know what this one is. That's what I'm looking for. So that's going to be something in degrees, but I know that's a diameter because it's going through the center. So 180 minus 55 minus 21 will give you 104 degrees. So this is 104 degrees. X in that scenario is 104 degrees. So same thing here. It looks like I'm trying to figure out what x is in degrees. These two are marked with one arc, so that means that those two are the same measurement. And since this is going through the center, I know this is a diameter. So if this side's 140, then that must mean that this piece right here would have to be 40 for it to be a diameter. And then if they're equal, then this other side is 40 degrees. Okay, here's our other one that said the theorem that we learned last time, that if you had chords that were equal distance from the center in the same circle or congruent circles, then the arcs were congruent. So this arc right here is congruent to this arc right here. So these two are the same. So if we're trying to figure out what x is in terms of degrees, I know that all the way around a circle is 360. So I'm going to subtract the 115 and the 71. That gives me 174, but that's between the two of them, so I'm going to divide that by 2, and I get 87 degrees for each of those. So 87 degrees for this side, 87 for that side. So x is 87 degrees. Okay, last one. We had that theorem that said that if you had a diameter and it was perpendicular to a chord, which this one is perpendicular to a chord, I can see that right here, then it bisects the chord and the arcs are congruent. Okay, well, this is a diameter. So if this arc is 130, then this arc right here must be 50. Since they're congruent, then x would be 50 degrees. Okay, and then the last two, they kind of line up with your homework where we draw the picture. It says if the diameter of a circle is 32 millimeters long and a chord is 26 millimeters long, how far from the center is the chord? I just like to draw these all the same. I like to use the theorem where if I have a diameter and it's perpendicular to a given chord, then it's the bisector of that chord. So this piece is the same as this one, and then I draw in a radius. Okay, now let's go back and put our numbers in that we know. If the diameter of a circle is 32 millimeters long, okay, so if the diameter is 32, then that must mean that the radius has got to be half of that, right? So the radius is 16 millimeters. So I'm going to put this right here in my right triangle. And a chord is 26 millimeters long. Well, the whole chord is 26, but we know it's bisected, so I'm going to put 13 right here in my triangle. How far is the chord from the center? Or, yeah, how far from the center is the chord? Okay, I'm going to do Pythagorean theorem. So 13 squared plus x squared equals the hypotenuse squared. So if I go ahead and do my algebra on that, I get 16 squared minus 13 squared, which is 87. So that means x is the square root of 87. So how far away is it? It's as a decimal. Square root of 87 is about 9.3 millimeters. Okay, and then this last one. If a chord is 18 feet long and is 6 feet from the center, what's the radius? Okay, so I'm going to draw my circle, put my center in, get my diameter in. I'm going to get it perpendicular to a chord. And I know this piece is the same as this piece, and then I just draw in a radius so I can make a right triangle. And now we'll go back and put the numbers in. If the chord is 18 feet long, so that means each part is 9, and is 6 feet from the center, so here's my 6 feet, what will the radius be? Pythagorean theorem. So 9 squared plus 6 squared equals x squared. So x is going to turn out to be, let's see, square root of 117, which is approximately 117, about 10.8, what are our units? Feet. So that radius is about 10.8 feet. Okay, new material. So this one, you have to know the difference between inscribed and central angle. So we have been doing a central angle, and I'm going to put a center here in this circle. Where do we think it is? About right here, maybe? There's my center. Okay, remember, a central angle vertex is at the center, okay? We're learning a new one called inscribed angle. The vertex is not at the center anymore. So remember, when we had a central angle, the measure of its intercepted arc, this right here, was the same thing as its inside angle. So if I said this was 80 degrees, then the arc measure was 80 degrees. That's what happened when we had a central angle. Okay, it makes sense to me then that this inscribed angle right here, it can't be 80 degrees. Look at it, compare the two. It's got to be less than 80. So how is that relationship figured out? Well, let's get all that out of there. It turns out that an inscribed angle is a half the measure of its intercepted arc. So if we were to look here at the bottom down here, and I said that the intercepted arc right here from A to C, let's put our center in our circle again down here. Let's put it right there. And I told you that the central angle on this one was 80 degrees. Then you would tell me the arc measure is 80 degrees because central angle and arc measure are the same. Well, it turns out that if it's an inscribed angle, so inscribed, remember, means that the vertex has to be on the circle. You have to pay attention to where the vertex is. Then this angle is actually a half of the intercepted arc. So a half of 80 is 40 degrees. So you have to pay attention to where the vertex of your angle is. Is it at the center or is it on the circle? That makes a difference. So here we go. We're going to put all the measures in that we can figure out given the given information. So I'm looking at this one right here, and I can see that 50 degrees is an inscribed angle. It intercepts this arc right here. So this arc measure is not 50 degrees. It's not a central angle. It's an inscribed angle. So that means this arc measure is 100 degrees. Remember, inscribed angles are a half of the intercepted arc. So then that must mean then if this is my intercepted arc here, this inscribed angle must be 24 degrees. Okay, it looks like I have a diameter because I have this chord going through the center of the circle. So I can figure out all the rest of the missing arc measures. This one, if from D to A is 100, then A to B would be 80 degrees. And if B to C is 48, and that's a semicircle, then I just subtract the 48 from 180, and I'd get 132 for the arc measure of D to C. Okay, this one says if two inscribed angles of a circle intercept the same arc, then the angles are congruent. Okay, well that makes sense. Let's see what that looks like. So this inscribed angle right here, angle B, its vertex is on the circle, so we know it's inscribed. And then this other angle right here, angle C, where its vertex is on, is inscribed. They both intercept this same arc. So if I told you that this arc was 50 degrees, then that would mean this would be 25, because remember, an inscribed angle is a half the measure of its intercepted arc. And then this side would be 25. They're both intercepting the same arc. Okay, so that makes sense then. They'd have to be equal to each other. That just kind of is common sense. This one says, can you name two other congruent angles? All right, let's erase all that stuff that we have on here, and we'll see if we can figure out two other angles. Okay, so we have angle B and angle C, so I bet we could do the same thing with angle A and angle D. Angle A, right here, I'm going to draw that kind of long, intercepts arc BC, and the same thing with angle D. It intercepts arc BC. So we could say then that angle A and angle D are congruent. Okay, so using the theorem that we just talked about, we want to figure out what x is. I'm looking at this, and I see that this inscribed angle intercepts, this given arc, and then this other inscribed angle intercepts the exact same arc. So that means then that these two angles are congruent. They intercept the same arc, so they're congruent. So I'm just going to put 2x plus 14 equals 5x minus 13. And then I'm just going to solve that for x. So let's see, we're going to end up with 3x equals 27. So x equals 9. Okay, over here there's lots of information. We may or may not need it all. There's more than one way to approach this. First thing I notice is that I do have a diameter right here. That's super helpful. And I also notice that I have an inscribed angle right here. This angle right here, 34 degrees, is inscribed. So if I double that, that means this arc measure is 68. Well, since I have a diameter, I guess I'll just go ahead and do 68 minus, or 180 minus 68, and that would give me 112 degrees. So x is 112 degrees. Okay, here's another theorem that just kind of makes sense. It's saying if an inscribed angle intercepts a diameter, then the angle is a right angle. Well, that makes sense, right? Because remember, the rule says that it's a half of its intercepted arc. So if this is its inscribed angle, and the intercepted arc is a semicircle, then this would have to be 90 degrees. It would have to be a right angle. And you could do that. It doesn't have to be drawn just in one spot. I mean, you could do that anywhere. You could draw from here to here. This intercepts. You can do all kinds of angles. It doesn't matter as long as the vertex is on the circle and it intercepts the diameter. That angle right there is going to be 90 degrees. Okay, so in this picture, it looks like I have a diameter and I have an inscribed angle, so I know this is 90 degrees. So I want to figure out what 2x plus 10 and 4x plus 20, I want to figure out how they relate. Now, they're not equal. I don't know. I mean, in some scenarios it could be, but not in this particular one because I don't know that this is an isosceles triangle. All I know is it's a right triangle. I don't know that it's a right isosceles. So the only assumption I can make that's true is that 2x plus 10 and 4x plus 20 have to add up to 90. That's all I know is true. Between those two angle measures, that has to equal 90, right? Because inside a triangle is 180, and I know that angle B is 90. So these two are complementary. This angle and this angle right here are complementary. They add up to 90. Okay, so let's just go ahead and do the math on that. So 6x plus 30 equals our 90. So 6x equals 60. So x equals 10. So now we found the value of x, it's 10. Okay, couple more vocabulary words just so that you can, if you see them, you'll know what they mean. So a polygon is an inscribed polygon if all of its vertices lie on the circle. So right here on the left, this blue triangle is considered inscribed because all of the vertices are on the circle. Okay, this is an example of something that is not inscribed. So if I draw a circle and I put one vertex here, one at the center, and then one back on the circle, that is not inscribed. Just because the triangle is inside the circle doesn't mean it's inscribed. In order for it to be inscribed, all the vertices have to be on the circle. Okay, and then the other vocabulary word is the word circumscribed. So circumscribed means that it's the circle around the outside of the inscribed quadrilateral. So I've kind of color-coded it here. So inscribed is the blue, and the red is the circumscribed. So those are two vocabulary words. In case they show up in a question, you'll know what they're talking about. Okay, so this one says find all the angles and all the arcs. So we could use any of our theorems that we need to try to figure it out. So I think I'm going to use, I'm looking at this and I see a bunch of inscribed angles. All those vertices are on the circle, so those are inscribed angles. So I'm going to kind of just highlight these a little bit so I can see what's going on. This 75 is inscribed. I'm going to draw it kind of long because it's all the way from B to D. That's the arc measure that's associated with it. So if angle A is 75, then this whole arc measure that I just highlighted has to be double that. So that has to be 150. So from B to D is 150 degrees. Well, I know from B to C is 70, so that must mean then from C to D has to be 80 degrees. So that kind of helps me out a little bit. What else could I do? I know that all the way around a circle is 360, so I could find this missing arc measure AB. I could go ahead and do that. I know that I have 360 minus 130 minus 70 and minus 80. That would give me 80 right here. Okay, so then it says, the only thing I don't know is angles B, C, and D now, those inscribed angles. I've got all my arc measures. So what I think I'll do is I think I'll just highlight. So once again, I'm going to highlight this. Here's angle B. It's inscribed. Notice that the arc that goes with that goes from A to D all the way to C. So that's 210 degrees. So you got to take 210, divide that by 2, and you get 105. Okay, we can do the same thing with angle C. I'm getting all these colors here. Hopefully this isn't getting too busy. I'm going to do angle C. So angle C is here to here, and it's inscribed all the way around there. So that's the same thing. That's 130 plus 80. So that angle right there must be half of that. That was 210. So this is 105 right here. And then I don't know if you know, but there's a theorem that says inside a quadrilateral, the sum of all of those angles is 360. So I could do an inscribed angle and figure out what my missing angle D is, just like we did with the other ones. Or I'll use that quadrilateral theorem, just because that's a nice one to know. So 360 minus my 105, minus my 105, minus my 75, and I should end up with 75. Okay, so let's go fill in our answers over here. So angle B was 105 degrees. Angle C was 105 degrees. Angle D was 75 degrees. The measure of arc AB was 80 degrees. And the measure of arc CD was also 80 degrees. And then it says, do you notice anything about opposite angles of the quadrilateral? Well, what you were supposed to recognize is those opposite angles are supplementary. So opposite angles are supplementary. So they add up to 180. So that leads us into our next theorem. So opposite angles of an inscribed quadrilateral are supplementary. Now remember, it has to be inscribed. It's not any, this is an inscribed quadrilateral. So that means if you've got a quadrilateral and all the vertices are on your circle, then opposite angles, so angle D and angle B would be considered supplementary. And then angle A and angle C, those two would be considered supplementary. So these two are supplementary, and then the other ones are supplementary. Okay, the other set. All right, so this one just says find all the missing angles and arcs. We can use any theorem we want. So right off, right in my head, we just did, if we've got an inscribed quadrilateral, then these opposite angles are supplementary. So 110 Opposite 110 would be 70 degrees because 110 plus 70 is 180. And then you can do the opposite is 78. 180 minus 78 would give you 102, or you could have done the theorem that inside a quadrilateral all four angles add up to 360. Either way. So now we got all the inscribed angles. Now all we have to do is find the missing arcs. So I think what I'm going to do is pick an angle that uses the 125 as part of its arc measure. So I think I'm going to look at this one right here, 110. So let's go ahead and draw that out long. Its inscribed angle and its intercepted arc are what's highlighted. So that means from here all the way over to here is 220 degrees. Now I know part of it's 125, so I guess I'm going to use 220 minus 125. And we're going to get 95. So this arc measure right here is 95 degrees. Okay, and I think I'll do it one more time. Let's do, I'll do the 102 since it's got the 125 in it also. So I'm going to do 102. So here's my inscribed angle right here. And its intercepted arc is from here all the way to here. So 102 doubled is 204. So this is 204 outside here. I know 125, so I'm going to do 125. The 204 minus 125. So my missing piece is 79 right here. So this arc measure is 79. And then all the way around a circle, remember, is 360. I could do another intercepted arc if I wanted, but I think I'll just go 360 minus 79 minus 125 minus 95. And that gives me my last missing arc, which is 61 degrees. Okay, so you can use any of those theorems you need to figure out what's missing. The key, though, is to make sure that you understand the difference between inscribed and central angles. So one more time. Central angles, the vertex is at the center. That's a central angle. If this is 60 degrees, then its arc measure is 60 degrees. They're the same. Inscribed angles have a vertex on the circle. So even if they intercept the same arc, they can't be the same measure. It's a half the intercepted arc. So that arc measure would be 30. So that's pretty important. Got to remember, where is your vertex when you're trying to figure out your arc measures? Where is your vertex? Keep that in mind.